In this lesson, we will be exploring the effects of horizontal stretches, compressions, and reflections on functions, and we will be applying this knowledge to analyze and graph functions. With that in mind, we're looking at comparing the following graphs. We have the parent function, y is equal to f at x, and we want to identify that as one of the parent functions we've already explored. Now, looking at that graph, that would be the square root function. So let's identify that first, because those points from our parent function are critical in deciding what has happened to each of those points. So f at x is equal to square root of x. Okay, so there's our parent function. Those key points are 0, 0, 1, 1, 4, 2, 9, and 3. Okay, so 0, 0, 1, 1, 4, 2. Okay, so the red graph represents our parent function. We want to know what happens if, so given the graph of y at x, compare it to the graphs of y f 2x. What does that 2 do to our function? Now, if you see here in the graph, we're given the graph of that function. And we want to observe, noticing that all the y values have remained the same. So 0, 1, 2, and 3. What are the corresponding x values when those y values are 0, 1, 2, and 3? So looking at the blue graph, when y is 0, x is also 0. When y is 1, x is actually 1/2. Interesting. And the parent function is 1. In the transformed function, it is 1/2. Then we look at when y is 2, the x value is 2. In the parent function, it was 4, and now it is 2. Likewise, looking at when y is equal to 3, my x value is 4.5. Each of the x values were multiplied by 1/2. Interesting. Moving on, let's see how are my parent function, it's the same parent function, how is it impacted when we're observing the graph y is equal to f 1/2 x. So again, the parent function key points for our square root function is 0, 0, 1, 1, 4, 2, 9, and 3, which is represented by the red graph on our grid. Looking at the blue graph, we want to observe again, the y values are remaining the same, 0, 1, 2, and 3, and what is happening to each of our x values. In this case, when y is 1, x is 2. When y is 2, x is 8. When y is 3, x is 18. So if we observe the x values, when we're looking at the graph y is equal to f 1/2 x, each of our x values were multiplied by 2. Interesting. With that, we can summarize in functions of the form y is equal to kx. So the number attached to the x, that coefficient, is represented by the variable k. If we look at that k value, if it is greater than 1, the graph is horizontally compressed by a factor of 1 over k. So that scale factor. So observing, going back to the graph, not to make you dizzy, going back to the graph, when k was equal to 2, okay, if you're comparing from y equals f at x to y equals f 2x, the graph was horizontally compressed by a factor of 1/2. Likewise, when we observe the graph of y equals f at x compared to y equals f 1/2 x, the graph was horizontally stretched by a factor of 2. each of those x values were multiplied by 2. So looking at those key ideas in the functions in the form of y equals k at x, we observed when k was greater than 1, the graph is horizontally compressed by a factor of 1 over k. And that's really important. That scale factor is that number we kept multiplying the x values by. If, however, the k value, so the number attached to the x, was a number between 0 and 1, which we know are fractions, the graph is horizontally stretched was by a factor of 1 over k. So note, this is important, the image of the point xy on the graph of f at x is the point x over k on the graph of k at x. So in simple terms, to transform the function with the k value, you're multiplying the x values by 1 over k. And I'm going to highlight that because that's very important. That represents our scale factor. So our scale factor is always 1 over k. K is that coefficient in front of your x, okay? What we have to do to each of our x values, because that's how we're going to be graphing, we're going to take those key points from our parent function and we would be multiplying each of those x values by 1 over k. So applying that to example 2, we're looking now at A, where y equals f negative x. So we learned from above to transform the function with a x value, just multiply the x values by 1 over k. So we know that the parent function we're dealing with, which is the square root, we know the key points are 0, 0, 1, 1, 4 and 2, 9 and 3. Right? In order to determine what the new function is going to be, we're going to take x and we're going to divide it by that k value. If we notice in this example A, k is equal to negative 1. So that would remain, the y's would remain the same. So we're going to take each of those x values and we're going to multiply it by 1 over k, which is the same thing as dividing it by that k value. So we're taking all our x's and dividing it by negative 1. 0 divided by negative 1 is still 0. 1 divided by negative 1 is negative 1. 4 divided by negative 1 is negative 4. And 9 divided by negative 1, which is negative 9. The y's remain the same. Oops, the y's remain the same. So it would be 0, 1, 2, and 3. And let's graph that. We do have our parent function already graphed with those key points, the 0, 0, 1, 1, 4, 2, 9, and 3. If that k value is negative, how does that impact our parent function? So at 0, 0, we remain the same. When x is negative 1, y is 1. When x is negative 4, y is positive 2. And when x is negative 9, oh, wow. So what we observe here is the function is reflected into the y-axis. What x values were positive, they became negative. So again, that would mean that they'd be the same distance to the y-axis. Let's see how the graph is going to be impacted when there's a value as well, not only a negative. So in this case, we want to identify the k value. So in this case, our k value is negative 2. So therefore, my scale factor, which is 1 over k, is going to be 1 over negative 2. That means all our x values are going to be multiplied by negative 2. So with that, we are going to keep in mind, we're going to start with our parent function and key points, which is 0, 0, 1, 1, 4, 2, 9, and 3. So we're going to take each of my x values and I'm going to divide it by negative 2, I can say, or it's the same thing as multiplying by negative 1/2. So keep in mind x times, so x times negative 1/2 is the same thing as x divided by negative 2. Okay, so that's just simplifying that. So therefore, all my x values, I'm going to divide by negative 2, and my y values would remain the same. So 0 divided by negative 2 is simply 0. The y values remain the same. 1 divided by negative 2 is negative 1/2. Y value remains the same. X, when 4 divided by negative 2 is negative 2. Y is 2. And 9 divided by negative 2 is going to be negative 4.5. And y remains the same. So when we graph that, I'm going to try a different color. We're going to say at 0, we're at 0. At negative 1, we're at 1. At negative 2, we're at positive 2. And at negative 4.5, we are at 3. Okay, so this graph has been horizontally compressed by a factor of 1/2, and there's been a reflection into the y-axis. Okay, so the key idea here, if k, the absolute value of k, is less than 0, then the graph is reflected into the y-axis. So reflection right into that y-axis. Okay, looking at example 3, we have the given graphs have the parent function solid line and a transformed function dotted line. Determine the equation of the transformed function in the form y is equal to f k at x. So we have to come up with the equation. So the dotted line would be the transformed function. The solid line is the parent function. Okay, so with that, I'm just going to identify so we remember the transformed, which is y is equal to f k x. And this would be y is equal to f at x. Going back to my blue. Okay, so let's start with, of course, our parent function key points. We know this is the absolute value function, so we're going to state parent function. That's always so important. Identify what function we're working with first. F at x is equal to the absolute value function. Okay. With that in mind, we want to list all those points. So we know x. We know we're going to say negative 2. We're at positive 2. Negative 1, we're at 1. 0, 0. 1, 1, 2, and 2. Okay, so with this, we know that the only transformation we have is either horizontal stretch or compression. So those y values would remain exactly the same. Okay, so let's see what happens with each of those x values. That'll help us decide what the scale factor is. In turn, that'll help us determine what the k value is. So with that, we look at when y is 2. So when y is 2, I'm going to go all the way over here. My corresponding x value is negative 8. When y is 1, my corresponding x value is negative 4. 0, 0, 4, and then positive 8. So we need to observe what is happening to each of my x values. How do we get from negative 2 to negative 8? Okay, so what are we doing to negative 2 to get to negative 8? Simply said, we're multiplying each of the x values for my parent function by 4 in order to get the corresponding x values in the transformed function. So the scale factor happens to be 4. That means we are multiplying each of my x values by 4. So keep in mind when we're coming up with the equation, that just gives us the scale factor. we learned that the scale factor is always 1 over k. So if the scale factor is 4, we're multiplying each of our x values by 4. We can replace scale factor by 4 and then cross multiply to figure out what that k value is, because that's what we need in order to come up with the equation of the transformed function. So we're going to take 4 times k, 1 times 1. So we have 4k is equal to 1. We need to isolate for k. That means k is equal to 1 over 4. Knowing that our k value is 1 over 4, therefore, the equation is y is equal to, in our case, because we know that the parent function is a absolute value function, we can say y is equal to 1 over 4x. Okay, looking at example 4, we have the function y equals f at x has been transformed to y equals f k at x. Determine the value of k for each transformation. A horizontal stretch by a factor of 3. So we're just practicing that idea. If the scale factor is 3, is equal to C3, we can say therefore 3 is equal to 1 over k, cross multiplying 3k is equal to 1. Divide that by 3 to get k by itself. K is equal to 1 over 3. Okay. What happens when we have a horizontal compression by a factor of 1 over 4 and a reflection in the x and the y-axis? So knowing that, we know if there's a reflection in the y-axis, the k value has to be negative. So again, the scale factor is equal to negative 1 over 4. So therefore, we can say, therefore, negative 1 over 4 is equal to 1 over k. Cross multiplying, we'd have negative k is equal to 4. And when I say cross multiply, divide this by negative 1 to get rid of that negative up front. So k has to equal to negative 4.